In this segment, we're going to come back to the task of part-of-speech tagging, now armed with HMMs, and see how they can actually do on real data and kind of compare them to other approaches. So to start off with, we're going to talk about the version of HMMs that actually works well for part-of-speech tagging. So what we've talked about so far is what I'm going to call a quote-unquote bigram HMM, where the states here are just single tags. Now, recall that HMMs make this Markov assumption, which is that the next step depends only on the current state and not anything in the past. And it turns out that this is a little bit too aggressive of an independence assumption. Instead, what we want to do is we want to be able to condition on stuff that's a little bit farther in the past. But kind of modifying the actual HMM model and algorithm is a little bit annoying. So instead, the way we can do this is we can think about changing our state space to actually be a pair of tags consisting of the current tag and the previous tag. So corresponding to this Fed raises example above, now the state for Y1 is going to capture this, kind of bracket S start of sentence symbol. And for Y2, it's going to remember that an NNP was the previous symbol here. So these transition probabilities are now these more complicated things that look at, basically transitioning to a pair of tags from a pair of tags. But one of these tags is always shared, right? Like if it's NNP in the kind of second position at the current time step, then at the next time step, it has to have NNP in the history here. So the transitions become more complicated, and there's certain optimizations that you might want to think about when actually implementing this, because only some of these transitions are legal now. But from the perspective of the rest of the algorithm, even though we have this more complicated state, everything else can kind of proceed as before. In particular, the emissions now condition on both on kind of both of these tags, the tag and its kind of history, and that's useful. So we could go farther. We could try to incorporate more of a history. It turns out trigrams are kind of the sweet spot for HMMs. Okay, so taking our existing tagger, we can apply this to the Penn Tree Bank data set, which is one of the earliest data sets that was created for large-scale English part-of-speech tagging. Now, there are part-of-speech data sets for a lot of languages now. We'll come back to those a little bit at the end of this segment. But the Penn Tree Bank data set has 44 tags in it. It turns out the baseline of just assigning each word its most frequent tag seen in the training data actually does very well on the test set. It gets around 90% accuracy. And the reason is, I think I mentioned before that we have tags for things like period in there. And then there's plenty of words like the and a, determiners, that never show up with any other tag. So you're always going to get these right. They're just totally unambiguous. Regardless, there are still a number of ambiguities, right? I mean, 10%, kind of 90% accuracy means that 1 in every 10 words is wrong. And so what that means is if we imagine a 20-word sentence, which is a fairly standard length sentence in a news article, we're going to have about 2 errors in that sentence is what we'd expect. So our trigram HMM can cut that error rate in half. It can take the accuracy to 95%. And in particular, it can get 55% accuracy on words that don't show up in the training set. Now, these are hard words because, recall that for this baseline, it actually wouldn't be able to say anything about those words, right? But the trigram HMM knows about the context, and so even though the emissions aren't useful for determining the tag of that word, it still can do something reasonable. So a kind of souped up version of this system due to Torsten Brandt's gets slightly higher accuracy overall, but much higher accuracy on unknown words. Christina Tutanova and Chris Manning created a maximum entropy tagger. So again, maximum entropy is kind of a synonym for logistic regression. And this is going to be more or less doable once we see CRFs. We're going to look at named entity recognition, but it's going to be more or less the same kind of system as they build here. And that does even a bit better. And this is actually not too far behind the state of the art. If you do kind of crazy stuff with ILSTM CRFs or BERT, you actually don't even get that much higher than this. You get around 97.5%, and you get higher performance on unknown words. So let's take a look at what some of the errors in these systems look like. So this is from the Tutanova and Manning work. And what they have here is a confusion matrix showing basically which pairs of tags tend to get confused between golds and predictions. So for example, what this cell up here means is that the correct tag was JJ, adjective. So that's what's on the the kind of left side here. And then the column means the erroneous tag that was predicted. So in this case, nouns. And the reason that adjectives and nouns can get mixed up is cases like official knowledge, where official can either be an adjective, meaning that it can be an adjective, or it can be a noun, like for example a government official. And you might think, okay, why would you ever have a noun in this context? Well, there's actually a lot of noun-noun compounds that have a similar structure. For example, tax cut, art gallery. Tax and art can't be adjectives. Tax can be a verb, but in these cases you would want noun-noun as the analysis, but here it's the knowledge has the property of being official. It's not like associated with like a government official or something. Here's another example. So this is a verb particle error, like made up the story. What is happening here is that up, again, is not a preposition. It's a particle. And made up is kind of this unit that kind of goes together. And up does not really have the spatial semantics that it normally does when it's associated with being a preposition. And so in this case, it gets analyzed as a particle, but of course, it's fairly challenging for a model to know that. And then a final case here is recently sold shares. They're kind of, without seeing more context, you actually don't know which of these two tags it is. If I said, I recently sold shares, that's VBD. That's just the straight up past tense of the verb. But if I said, he has 50 recently sold shares, that means these shares were recently sold. We don't know by who. And that's a participial usage of sold. So again, so you can see that these errors can get kind of tricky here. And so Chris Manning in 2011 wrote a paper called Part-of-Speech Tagging from 97% to 100%, Is it time for some linguistics? And looked at the remaining errors in part-of-speech data. So one of the tricky cases that we've talked about is when you have a word that words that aren't seen. But another tricky case is where you have a word that has been seen, but it shows up with a new tag in the test set, right? And this is very hard to generalize to, because generally you're going to assume that, okay, we've seen this word before and we've seen it as a verb. Most likely it is going to be a verb. So this accounts for around 5% of the errors. Unknown words are also around 5%. In his analysis, around 15% of the things were errors that models could get right. Maybe you would need a better model, but it's at least doable. 20%, he said, had quote-unquote difficult linguistics. And so here's an example of that. They set up absurd situations detached from reality. The tags here differ on whether set is past tense or present tense. And you don't know, without seeing more of the context, whether this happened in the past or the present. And so we would have to think about models that go beyond a single sentence. That's much tougher, and so we're not going to do that. And then what he found was that 60% of the remaining errors were things that were either underspecified or unclear in the text, or the gold standard was inconsistent or wrong. And so here's an example of the kind of unclear case. a $10 million fourth quarter charge against discontinued operations. This is a case of a participial usage versus an adjective. Do the operations have the property of being discontinued, or are we saying that like these operations were discontinued? It's almost difficult to describe what the semantic difference between these two cases is, because in order for something to be discontinued now, it had to have like been discontinued sometime in the past, right? So this is the kind of ambiguity that you writing this or someone reading it may not even resolve for themselves. And so how can we expect a model to necessarily come to a decision about one of these tags to use here? Okay, so I'm going to switch gears a little bit and talk about a different way of producing part-of-speech tags, which is coming back to using neural nets here, and in particular feed-forward neural networks. So rather than appeal to part-of-speech, these like HMM taggers, we can instead go back to this idea of using something that looks more like a classifier. We can take these words around the word that we're tagging here. So we look at the previous word, the current word, the next word. We embed them into vectors. We concatenate those into a feature vector here, and then we're going to put that into a neural network. And so again, what we're doing here is we're being very careful to capture this position-sensitive information. We're looking at the previous word, the current word, and the next word. We're not using some kind of bag of words thing or that deep averaging network where you like add everything together. Here we're concatenating these three vectors. And so Jan Botha et al. Looked at this for a number of NLP tasks, and they did something a little bit more clever, which was they also looked at bigram and character bigrams and trigrams, and had a way of incorporating those into the model as well. And then that all gets kind of mixed together in a hidden layer, and then the model makes some sort of prediction. And this actually turns out to work pretty well across a whole range of languages. So they compared it to previous work that was doing recurrent neural networks and found that it was better than that work. And you can see on the right here that across a whole bunch of different languages, the accuracies are at least above 90% in all cases. Again, the kind of the error rates differ a bit. And this isn't comparable to the other data that we were seeing because it's a new data set and a different part-of-speech tag set. But the kind of general principle here is that these kind of models that we've built up so far can be used for lots of different languages, and kind of using this feed-forward neural network version of them can be fairly effective. So that gives you a sense of what a few models for doing part-of-speech tagging are that work basically as well as the fancier stuff that we're going to come to later in the course, things like recurrent neural networks and BERT. So now you kind of understand where the state of the art is in this area and what some of the strong models are doing. That's the end of this segment.